Okay, so this talk is about universally optimal streaming algorithm for computing random walks. This is joint work with Klim, Efremenko, Gillat, and Raghuvansh Saxena. Hey, so first, let's be specific about what's the problem we are considering. So the input is pretty simple. We are given a directed graph G and a starting vertex V0 for the random walk. And the output is an L-step random walk starting from V0. And we want it to be given as a sequence of vertices, V0 through VL. And the edges will be given in a single pass of stream. And it's an insertion only stream, so we don't allow edge deletions here. And for the correctness requirement, we want the distortion of the random walk to be at most, say, 0.01. And here, the distortion is defined as the statistical distance between the true random walk distribution starting from V0 and the output distribution. And here, the constant does not matter that much. We can either have 0.01 or say 1/3 or any other constant. Okay, first let's start from a Faulkner algorithm, which is pretty simple. So we can just sample L neighbors for each of the vertex during the stream. And after the stream, we'll just simulate this random walk from V0. And this is possible because at any time of the random walk, we can always pick the next sample vertex for the current vertex. And we will never like run out of neighbors because we are sampling L neighbors for each vertex, and this is an L-step random walk. So this algorithm is always having distortion 0, and it uses space roughly n times now. Okay, so the natural question we want to ask is, can we do better? Can we beat this photo algorithm? Unfortunately, by this paper in 2019, due to Zhang, this is impossible, at least for general graphs. So there is a lower bound of n times L roughly. But still, there actually is some hope to beat this Faulkner algorithm because we realized the proof of Zhang uses very low degree vertices. So what if the graph is somewhat dense, say in the sense that the minimum degree of every vertex is at least d? Can we do better? So here comes our first algorithm, pi1. We can actually sample only roughly L over D neighbors for each vertex instead of like L neighbors. And still we can simulate the random walk starting from V0 after like, the stream finishes. The only difference is that this time the random walk might fail in the case that at some point of the random walk, the current vertex is running out of sampled neighbors because some vertex may be visited more than L over D times. However, by standard concentration bounds, we can show that every vertex is visited no more than roughly L over D times log n times. And this holds like actually with high probability for all vertices at the same time. So this means that distortion of the new algorithm pi1 is only polynomially small, but we use like much less space, which is n times L over D, because now we only sample L over D neighbors for each vertex. But there's a catch here. This concentration analysis only works if L is much larger than D, because otherwise the concentration would not hold. And in particular, this means the space usage of this new algorithm pi1 will always be superlinear because L is required to be larger than D. Then the next question we want to ask is, can we do better if L is smaller than D? And specifically, can we actually achieve sublinear space when L is smaller than D? And it turns out this can't happen. We have another algorithm, pi2, where we want to sample L different layers of vertices. Like for each layer Vi, we'll sample a subset of vertices Vi, which is of size roughly n over d. And during the stream, for every layer and every sampled vertex for that layer, we'll sample just one edge starting from this vertex to any vertex in the next layer. So once the stream finishes, we will still simulate the random walk starting from V0. But this time, since for every vertex, we just sampled one edge going to the next layer. So there's a unique path starting from V0. And we'll just output this path as the random walk. And again, this algorithm might fail, but only if at some point of the random walk, let's say it's currently at the ith layer, this current vertex Vi, if it's all its neighbors are not sampled in the next layer, then we'll fail. Otherwise, we can keep going. And again, by concentration analysis, we can show with high probability every vertex has at least one neighbor being sampled in the next layer. So the random walk will go from V0 to the first level, the second level, and all the way to the Lth level. And again, the distortion is polynomially small. And the space usage is also n times L divided by D because we are sampling L layers of vertices, and each layer is of size roughly n over D. And again, I want to emphasize that if L is much smaller than D, then the space usage is indeed sublinear for this new algorithm pi2. So now that we have two different algorithms, pi1 and pi2, we want to compare them a little bit. First, we see pi2 uses the same space as pi1, which is NL over D. And second, more importantly, pi2 also works for L larger than D. So it works for basically any combination of L and D, whereas pi1 only works when L is at least as large as D. So is pi2 always better than pi1? Because if this is true, then there's just no need of pi1 at all. We can use pi2 for all combination of L and D then. For that, let's just see a very tiny modification to the algorithm pi1. We'll call this modified algorithm pi1 prime. So now instead of sampling L over D neighbors for every vertex, we'll just sample the minimum between L over D and the degree of V, that many neighbors for each vertex V. So this makes sense because if the degree of V is even smaller than L over D, then we can just store all those neighbors and we won't use more than that many space. And this can be achieved by like using a separate counter for each vertex to keep track of its degree. So we are not using more space. And now here comes a very simple example where we have a clique of roughly root n vertices. So each of them has degree root n. And all the remaining vertices will be connected into a path. So in particular, this means the minimum degree d will be a constant. Now suppose we want to generate a root n step random walk. Then for algorithm pi2, the space usage is n times L, which is root n divided by d, a constant. So it's n times root n. However, for this new modified algorithm pi1 prime, the space usage is only order n because we basically store all the edges. So this means, at least in some cases, pi1 or pi1 prime is significantly better than pi2. So it's still useful. So now one may wonder, is it possible there is another algorithm, pi3, which is better than both pi1 and pi2 for some input? And so here comes our main result of this work. What we show is that if we combine pi1 prime and pi2 just into a single algorithm pi3, which like run pi1 prime if L is larger than D, and otherwise just run pi2. We show that pi3 is actually universally optimal. So here, just for those of you who are not quite familiar with different kind of optimality, uh, the most standard or the most common optimality is called the worst case optimality, or it's sometimes also called existential optimality. And on the other hand, you also have instance optimality, the strongest form of optimality, which requires the algorithm to be optimal on every input instance. So here in the streaming setting, an instance means a specific input graph and a specific order of streaming the edges. However, this instance optimality is usually too strong or even impossible to achieve in many cases. So we also have a trade-off, which we call universal optimality, where we require the performance of the algorithm to be at least as good as any other algorithm on every specific input graph, but only over the worst case stream order. And just as a side note, I want to mention that this notion of universal optimality actually appears elsewhere in other contexts. For example, in the classical graph algorithms, universal optimality usually means the algorithm is optimal for every graph topology, but only over like the worst case assignment of edge weights. But as far as we know, we are the first to introduce this notion of universal optimality to the setting of like streaming algorithms. Next, in the rest of this talk, I'm going to give a very brief overview of how we prove a streaming algorithm is universally optimal. The first step, let's start with the worst case proof. So the hard instance is roughly as follows. We have a bunch of top vertices v1 and another bunch of bottom vertices v2. And you also have a set of like special chosen vertices v prime, which is of size exactly d. And there are two types of edges. So for E1, each top vertex V1 is connected to D random bottom vertices. And for E2, every bottom vertex is connected to all the chosen vertices in V prime. And the stream is just the edges in E1 followed by the edges in E2. And to see why this is a hard instance for streaming algorithms, here are some intuitions. So suppose the random walk starts from some vertex at the bottom. The first step, it will take some edge to a random chosen vertex in V prime. And then in the second step, it will take a random out edge of this vertex. So it goes back to some vertex at the bottom. So this means every two steps of a random walk, it will use a uniformly random edge in E1 going from V prime to V2. And so overall, we know that the random walk will use at least omega of mean between L and D squared different edges in E1 going from V prime to V2. So here L is because this is an L stat random walk, and D squared is because we have D chosen vertices in V prime, and each of them has degree D. So we can also write this as V prime, or the size of V prime, which is just D, times mean of L over D and D. So this basically means for every chosen vertex on average, we need to remember roughly mean L over D and D that many edges. So now if we choose V prime to be uniformly random among the top vertices V1, this time remember since the edges in E1 are streamed first, so the algorithm has no way to predict like, which vertices belong to V prime actually. So this means the algorithm can only just remember mean L over D and D that many edges for all the top vertices. Or in other words, the algorithm needs to store roughly omega of the size of V1 times mean of L over D and D that many edges in E1. And we can write this also as the summation over all vertices in V1 of the minimum between L over D and the degree of the vertex, which is just D. But if we can see this is just the upper bound we get from our algorithm also. So in order to turn this intuition into a formal proof, we'll use a standard reduction from commutation complexity. So we have a like one-way two-party computation problem where Alice will have the address in E1 and Bob will have the address in E2. And Alice can only send a single message to Bob so that Bob needs to output omega mean of L comma D squared different edges in E1 going from V prime to V2. And use a like standard information theoretic argument. We can show that the message going from Alice to Bob needs to reveal at least this much information about the edges in E1. And this is exactly the lower bound we can get from this. Okay, so now how can we translate this existential optimality lower bound to a universal optimality lower bound? So first, notice that what the commutation lower bound actually shows is the space requirement for the streaming algorithm right after receiving all the edges in E1 is at least, say, some amount. This is because we're cutting the stream into two halves, E1 and E2, and giving them to Alice and Bob, respectively. So the commutation lower bound corresponds exactly to the space lower bound right at this point. So this also implies that for any graph G that contains E1 as a subgraph, the same lower bound still holds if in the stream E1 is given first. So for our purpose, this means we want to know if for any given graph G, can we find a large subgraph that looks like or is similar to E1? So if this is possible, then we might be able to obtain a similar lower bound for any graph G, not only the hard instance graphs. And so here is the main technical lemma of our work, which shows that for any graph G, we can actually find a subset of vertices V1, which roughly satisfy the following properties. So first, V1 is not too small. Second, for every vertex in V1, it has at least a constant fraction of its all degrees going to like the complement, the outside. So if we go back to the worst case instance here, this actually corresponds to saying, okay, every top vertex has a lot of outgoing edges to the bottom vertices instead of like within V1. And there's a third property, which basically says the summation of the degrees within V1, or the summation of the capped degrees to be specific, is at least a large fraction of the total degrees. So this is required because we want the subgraph to be large so that a lower bound that we obtained in terms of the left-hand side summation will be translated into a lower bound in terms of the right-hand summation for the original graph. So this third item is indeed required. Okay, so this lemma is quite technical, but at a high level, the proof is just an instance of probabilistic method. So I'll skip the details here. But once we have this lemma, we can actually just define U1 to be a union over the vertices in V1 of a random subset of the edges going from the vertices in V1 and to the complement. This will be our hard instance. And fortunately, we can use a quite similar information theory argument to obtain like a very similar communication lower bound and translate it into a streaming lower bound. And finally, before I stop, I just want to mention a few like issues which is quite subtle, but is still very important to our proof. So the first is that in the original proof, the lower bound actually relies on all the top vertices having the same order degree D, because we want the random walk to use a uniformly random edge in E1. And this is not true if the order degrees of the top vertices are quite different. So this can be fixed by like partitioning all the vertices into like different intervals where in each interval the degree of like vertices are different by a factor of at most 2. And since there are only like at most log n different intervals, we can just pick the dominant one or the heaviest one. So, and by only considering the vertices in that specific range, then we can still apply a similar argument. And yes, we will lose a factor of like log n in the lower bound, but that is okay with us because we consider an algorithm to be universally optimal as long as its space usage is as good as any other algorithm up to logarithmic factors. And second, there's another issue that since we are only finding a subgraph of the given graph G, so these chosen edges E1 on its own does not guarantee the minimum degree to be at least D for all the vertices. So this means we are actually giving an invalid input instance to the streaming algorithm. So to solve this, we have to slightly modify the edges in E2. So this time we'll add a click C of size roughly order D. So remember the edges in E1 is going from the top vertices to the bottom vertices. So these edges remain unchanged. But now we have all the vertices connected to every vertex in the click C by edges in E2. And previously in E2, we have all the bottom vertices connected to all the vertices in V prime. Now we will just connect every vertex in C to every vertex in V prime. And now let's see how a random walk looks like. So suppose the random walk still starts from some vertex in V2. So the first step, it will just go to a random vertex in the click C. And for the second step, it might either stay within C or it will go to a uniformly random chosen vertex in V prime as usual. And this actually happens with probability at least, say, 1 over log n, because the size of C is order D, and the size of V prime can be chosen to be at least, say, D over log n by our technical lemma. So this happens with probably at least 1 over log n. And suppose this happens. In the third step, the random walk will either go back to C, or again, with probability at least 1 over log n, it will choose a uniformly random edge in E1 and go back to some vertex in V2. So this means for every 3 steps of the random walk, it uses a uniformly random edge in E1, as in the original case. Or in other words, every, say, log squared or polylogarithmic steps of the random walk, a uniformly random edge in E1 is guaranteed to be used. So overall, this means we will lose a polylogarithmic factor in the lower bound, but still a similar information theoretic argument will give us a similar lower bound. So we are good with all the vertices having degree at least D now. Okay, and that's all for the proof.